The next section of our notes is on factoring. Okay? Factoring is the reverse or inverse of multiplying. So it's kind of like dividing for algebra. And when we factor, so our 4x plus 8, and unfortunately you've already learned this, there's going to be a number in front times by something else. We're going to change something that's a full answer to write it as two things that are multiplied together. And so here, what was in common with the 4x and the 8 is a 4. And what would you be left with inside? X plus 2. So I already showed you this, and so in a way you already know how to factor. Okay? What factoring does is it changes something that's a total answer into two things that are multiplied together. One way of visualizing that is with algebra tiles. So algebra tiles that you've done them in grade 9. A little reminder, do you remember drawing, I think I even have beautiful algebra tiles built into here. Let's see if I can find them. This is not looking good. Where is my search here? Algebra tiles. Does that search? No. Let's go tiles. Does that search something? I used to have them saved. Pictures. No. There we go. I'm going to steal this x and this negative x for later. And I'm going to steal that x squared and this x negative x squared. You remember these algebra tiles? Folders, related folders, algebra. Maybe that would be the folder to find them in. There's my 1, and there's my minus 1. Well, maybe I'll use x and negative x labeled. Perfect. I'll get rid of this one. Nice. So there's some algebra tiles. I personally like my x tile. Did you draw it this way or did you draw it this way? Yeah, I like it. I don't know. Something about having it this way. Just so much nicer, right? All right, we'll put the negative x over there. We're going to make these nice. So we've got our algebra tiles, and I'm cloning them right now. Personally, I would have liked if they would have made the 1 green. I don't like the color. Not that I don't like red, but red, some textbooks use red for negative and green for positive. You know, like green light, red light kind of thing. So I would have liked it all to be green, but it's okay. So what we have in algebra tiles is 4 of these. 1, 2, 3, 4 of these, and 8 ones. 1, 2, 3, 4, 5, 6, 7, 8. And with algebra tiles, one of the things that you can do for factoring is say to yourself, is it possible to arrange these 4 x tiles and those 8 1 tiles to make a perfect rectangle? And what would it look like? Perfect rectangle. So like if I put these together, like this, right? That's a perfect, altogether makes an area that's a rectangle. If I put these 1s off to the side here, what's the problem with trying to do the 1s along the x side? You don't know how big x is, so they never, oh, does this match up? It's not supposed to. It's not supposed to match up. It almost looks like it does. But if these are well-designed algebra tiles, they don't match up. But it would match up if I put them here, because that matches up perfectly. 2, 3, 4, 1, oh my goodness. 2, 3, 4. Now you're not going to use algebra tiles very often because you've already learned the shortcut way. But with algebra tiles, what we've done is we've made a rectangle. This rectangle has an area that's equal to 4x plus 8. How long is this side, and how long is this side? Oh, because what do we know about area? Area is equal to length times width. So our area, which is 4x plus 8, is equal to, how long is this? 4, well, 1, 2, these are just 4. And how long is this? X plus 2. Okay? So if we use our algebra tiles, we can make an area, and if we can make a rectangle, we can look at the length and the width to figure out what would be the factoring for it. Now, one of the things that you guys started with when we did this, some of you came up with this. Do you remember the very first example? I mean, we didn't have these exact numbers, but some of you came up with an answer like this. And I said, yes, that's right, but it's not factored completely. Can you see that it could also equal 2 times 2x plus 4? I mean, if I rearrange this, I could also make a rectangle this way.
So we want the rectangle that's closest to cube as possible?
We want the rectangle that is as closest to a square, I guess. Because another way you could do this is you could, right? And you'd have 1 times 4x plus 8, which is also equal to 4x plus 8. But when we factor it, what we're looking for is the one that pulls out the biggest number possible. Now, the algebra tiles just give us a connection to see how does area relate to factoring. And you can do that with other numbers as well. I mean, if you have 56 of these little ones, what kind of rectangle could you make?
56.
If you have 56 of them, what kind of rectangles could you make? You can make a 7 by 8, right? You could make a 2 by 28. You could make a 1 by 56 if you wanted to, right? There'll all be rectangles, and the area still represents the total that you have. All right, so what did we do? We moved our tiles into the most compact rectangle that we could, and then once we had that rectangle, we looked at the length and the width to figure out. Of course, you guys are already good at factoring, and you could factor ones that you could do even without tiles, right? Because sometimes I used S's and T's and all sorts of complicated stuff on Friday. And you don't have tiles for that, but that's okay. So here, we're going to steal an x squared and 6 x's. So I'm going to take that one, I turn it on its side. Clone each of these. So first of all, if you're already capable, that's great, because this, you're not going to draw out pictures every single time, but the pictures just help us see what would happen. If we wrote this, what could we pull out? A 2x. That's the biggest number, the greatest common factor between the 2 and the 6. And then when we look at the variables, we say, what variables do they have in common? Both of them have at least one x. If I say now, if I multiply what's left inside, I would need an x here so that this would make 2x squared, and I would need plus 3 here, so that makes 6x. If I take this, whoa, I didn't clone it. There we go. If I take 2 of these, maybe I'll take them and I'll put them this way. If I take 2 of these and I want to make a rectangle and I need 6 of these, 1, 2, 3, 4, 5, 6. Did you know that that's how the algae tiles were actually made? That this x squared tile is an x squared because it has an area of x squared, because this side is x and this side is x. And the area would be x squared. And the x tiles have an area of x because this side is x and this side is 1. And x times 1 would give an area of x. And so the total area of 2x squared plus 6x would be this. And if I look at my length, this is x plus x, this side would be 2x. And if I look at my width, this is going to be x plus 1, 2, 3. And so our algebra tiles show us the factoring as well. That 2x squared plus 6x is equal to 2x times x plus 3. Are there other rectangles we could make? Yes. We could have just made a long rectangle. Can you see if you made the long rectangle, that would have one side as x, but the other side would have 2 x's and then 6 1 tiles in a row. The interesting thing with this, you could factor out a 2, right? I can do this. But I can't make a rectangle with that. That's interesting. Not with the tiles that I have. All I could do with that is make x squared plus 3x's in one group and x squared plus 3x's in another group and say I have 2 of those groups. Which is the best answer? The best answer is the one where you factor out everything that's in common. So when we factor, which is the reverse of multiplying, right, there could have been a number of different ways to get 2x squared plus 6x, but we're looking for what's the way where we could pull out the biggest or the greatest common factor out of all of the terms. So here, that's algebra tiles. We don't have to do that very often. How do we factor something fully without algebra tiles? We're looking for the greatest common factor for both the numbers and the variables, and then write it as a product of our factors. So I think what we did on Friday, right, if I just tried to teach you this today directly, you'd be like, oh, look at all the instructions, all the stuff I have to remember, like greatest common factor. But I think you have a sense, yes, of what's going on. I hope so. So what's common between the 2 and the 4? A 2. What about the variables? X squared. Excellent. And what are we left with? Well, we have to imagine what would have to be here to get me my 2x cubed. There's just an x left and plus 2. So I'm going to come around and check with you guys. Okay, there are 1, 2, 3, 4, 5, 6, 7 factoring questions for you to do, starting with this one. I'd like you to do them on your own, and I'm going to check how things are going. In this first one, there are two possibilities for an answer that would be correct. You could either say, I see that there's a 3y in common, leaving me with negative y squared plus y minus 2. Or you could have taken out a negative 3y, leaving you with positive y squared minus y and plus 2. So you have an option in this case. Sometimes it makes sense to factor out the negative as well, or sometimes it makes sense to leave the negative inside. In both of these cases, I would give you that correct. Did you get one of those two answers? Whew, whole bunch of letters, but you did these ones as well. Look at the numbers first. Is there something in common, a common factor of 6, 8, and 2? Yes, it's a 2. Then look at your variables or your letters. Are there letters that are in each of them? B and C. So then we ask ourselves, what is left? If I've taken out a 2 and a B and a C, we imagine, what would I have to multiply here to get 6? I would need a 3. And in order to get A, B, and C, well, I've already got the B and the C, I'm going to need another A. Same thing in the second term. I need a plus 4 to get plus 8. I have the B and the C, but I still have a D left. And the last one, I need a negative to make it negative 2. But the B and the C are already there. What do we do when everything's there? We have to imagine, what would multiply here to get negative 2BC? I would still need a 1. It doesn't matter what order you put the stuff in the brackets. However, generally, we write it in the same order so that if we looked at the arrows, the first ones match up with the first one, right? The first ones match up with the first one. The second one matches up with the second one. And the last one matches up with the last one. But the order doesn't matter because is 5 plus 3 different than 3 plus 5? Does adding matter the order? No. Right? And that can be a really good strategy if you're adding up something that looks really difficult to add up. If I was adding this up, I'd add the 33 and the 67 first. Why? That's easy. What does it make? 100. And how hard is it to add 100 to 2,187? Pretty relatively easy. But adding the 33 to the 87, you got some carrying, you go, oh, right? Your mind starts to get a little bit difficult. So knowing that you can add things up in different orders can be helpful. Anything in common here? A 6. You might have seen that the 2 was in common first, right? But we're always looking for, is there a bigger number? Now, I'm going to say, yay if you saw the 6 first. 3p cubed plus 2. But what happens if you don't see the 6 first? Can you still do this? Yes. Let's say, oh, Mr. JR, I saw the 2 first, so I took that out, and that left me with 9p cubed plus 6. That's not wrong, but it's not done yet. Because if we're going to factor something completely, we still look inside, and now you see the 9 and the 6, and you ask, is there anything in common with a 9 and a 6? A 3. So right now we have 2 times this. If I pull out the 3, I would have 2 times, and now I have 3 times 3p cubed plus 2. What's 2 times 3? 6. Can you see that we got the same answer that we got directly over here? It just took us a little bit more time.
Did you just pull out the 3 out of nowhere, like common sense?
I pulled this part here is equal to what's underlined in blue. So I looked inside the brackets and said, oh, there's still a 3 in common between those two terms.
Oh, so you found the most common, lowest common factor?
The greatest common factor. I could put this in brackets like that. And I did it in 2 steps because I didn't see the 6 right away. So one of the things we want to sort of train ourselves to do is we want to see, is there anything in common? If there is, pull out the biggest thing I can. But once I'm done, I should check, did I miss anything? If I look at 3p squared plus 2, no numbers in common, good. No variables in common, good. I'm done. But had I pulled out the 2 first, because for whatever reason my 6 multiplication table was on holidays that day, and all I could see was the 2. Then I look inside, and now I have 9 and 6, and I go, oh, good thing my 3 multiplication table isn't on holidays today. I can pull that out. And then I realize in the end, oh, I could have pulled a 6 out right from the beginning. Where does this happen more often? Is if I give you really, really big numbers, right? Like if I gave you, here we'll do question B.5, huh? Right in between B and C. If I gave you 27x squared y plus 81xy cubed, when you look at 27 and 81, what number do you see that they have in common from your times table? 9. Good. So you take out the 9. What variables? What would you take out? xy. And what would that leave me with? It would leave me with 3x plus 9y squared. Is there anything still in common inside after you take out the 9?
Yes.
Yes, a 3. Okay? And I chose these numbers, so now I'm going to put a big brackets here because I'm going to factor this. This would be, I pull out a 3, leaving me with x plus 3y squared. Can you see in the final bracket that there's nothing left in common? But now I pulled out a 3. What would be the way I should write this? 9xy times 3? Well, I can do 9 times 3. 27xy, x plus 3y squared. I chose the numbers purposefully because I knew you could see 81 was 9 times 9, and I knew that you would see 27 was 9 times 3. But I was pretty certain that many of you hadn't practiced your 27 times table yet to know that 81 was 27 times 3 right away. True?
Yeah.
So this shows you if you don't see the greatest common factor right away, it's not the end of the world. In fact, partially factoring it makes it easier to see it later. Oh, I still could have factored out a 3 in the inside to make it 27. All right, that was B.5. For C, you look at the numbers. Could you see you could pull out a 2, and if you look at the variables, you can pull out an x squared plus 2x plus 4. Every time I factor, I know you don't see this because I do it in my head, but every time I factor, as soon as I'm done, my brain does this. And mental math checks. Is 2x times x squared 2x cubed? Yes. Is 2x times 2x 4x squared? Yes. Is 2x times 4 8x? Yes. The next mental math thing my brain does is it says, check on the inside. Can I do anything more with this? Is there anything else in common?
I'm just kidding. No, I take it back.
Oh, you're just, and if the answer is no, then you would be done. Later on, what's going to happen is you're going to have to check this, right, to see if you could put it in 2 sets of brackets like we had before. But this one you can't.
Why would you want to?
Whew, you want to go all the way to where this is all leading all at once?
No.
Okay.
No. Abort.
Abort?
Abort.
Okay. Because we're developing. See, this is the crazy thing about math. Right now, you're asking that great question. Why would we want to do this? Because it seems like we're just fiddling with stuff, right? We are, right now, just fiddling with stuff. Is there reasons for this? Yes, lots of them, tons of them, but I'd have to teach you all the way to grade 12 math just to show you some of them, okay? So sometimes what we do in a math class is we develop tools. Factoring is one of those tools. Probably if you would put it on important tools, right? This would be one of those important tools. You open up your toolbox and it's like, is the screwdriver an important tool that I'm going to use around the house? Or is the high-powered nail gun something I'm going to use a lot? Well, the high-powered nail gun might be fun, but it's going to cause a lot of damage. You're not going to use that a lot. The screwdriver, every time you have to fix something, it's like, oh, I need a screwdriver to fix this. So factoring is one of those tools that we're going to have in our toolbox that's going to be very important. But you don't want to know all of it right now, and that's fine. But please understand that this is one of the most important skills moving forward that we're going to have. So we want to get really good at it. And if you really want to, I can show you some of the things coming up in a bit. But right now, let's just make sure we've got all of these ones correct. You can pull out an M and an O. Second attempt at drawing an N. Perfect. That would leave you just with 1 plus 2. There'd be 1 M left and 1 N. Technically, it doesn't matter the order you write your variables, but in unwritten math fashion, if you have more than one variable, you'll write them in alphabetical order. So it should have been M squared N squared if this was really nicely written. $15, $21, and 6. What number do they all have in common? 3. Look at your variables. Do they have any variables in common? An S and a T. Leaving me with 5 for the first one. Good. Minus for the second one, minus 7. 1 more S, 1 more T. Plus 2. 2 more S's. Number in common? 6. Letters in common or variables, we have 1 X in each of them. We have 1 Y in each of them. So what am I left with? I'm left with 2 X's and 1 Y in the first one. Minus 2, that's all for the second one, plus 5, 1 more X, 4 more Y's.